In this tutorial, we will learn to perform analysis and explore the resulting graphic and text output. We will continue from the exercise of previous tutorial where we learnt about meshing for rain screen cladding. Corresponding files for this tutorial are also available to download from the link mentioned in the comments. In the previous tutorial, we have already created grid meshes using auto grid generation. Even if we performed fill blocks or fill grid or fit grid previously, upon opening SOLIDO, it would default be in wireframe mode, so we need to reperform fill blocks or fill grid to visualize the rasterized geometry. Now from the Edit menu, choose Derived Thermal Properties. Here choose 2D, 3D surplus thermal transmittance to calculate the additional heat flow because of 2D, 3D thermal bridging. By choosing this, the software would also calculate the equivalent U value. Equivalent thermal transmittance is calculated from the equation shown here. To perform this calculation, we need to know the areas of flanking element and 1D U value. From the Edit menu, choose Areas. Here we see the area of the flanking element. Upon selecting the cell, we visualize the surface area by highlighting it in the image window. Now at the Edit menu, choose U values. It's easier to define 1D U values with a minimum grid, so from the Edit menu choose Minimum Grid. From the Blocks menu, toggle on Grid Number Coordinates. Then the U values window updates to absolute numbers, which is the fraction of the total dimension along each axis mentioned in the grid window. We see here that the height of geometry is 90 centimeters. Say we want to calculate the U value at height at 20% of geometry height, then change the values of Z1 and Z2 to 0.2. The 1D U value is to be calculated along the edges of the wall. Say we calculate it along the edge which passes through the origin. So, the values of x1 and x2 are 0. For a ventilated facade, as per the standard EN ISO 6946, the 1D U value will be calculated from the indoor boundary to the highly ventilated cavity. So for y1, which is a point inside the cavity, say 0.1, which means 10% of the total length of geometry along the y-axis. Then y2 will be 1, as we calculate till the end of the indoor boundary condition, which is 100% of y length. You can now also see the vector along which the 1D U value will be calculated. Now the other parameters at the bottom rows will be 0, as we have only a single 1D U value to be calculated. If in case we had multiple flanking elements, we should use a similar procedure and calculate them. Finally, from the Grids window, choose Auto Grid Generation and Split Ratio as 1.3 to get a bit finer grid mesh for analysis. As the grid window updates with the auto-generated grid mesh, we notice the U value window also updates to be coherent with the new grid mesh. You can now close the U values window. The object is currently under the wireframe. So, click on Fill Blocks to generate triangulated mesh, Fill Grid to rasterize and then Fit Grid. You now click on the Calculate system to run the analysis. Once the calculation is complete, you can visualize the resulting temperature gradient. We can run the calculation immediately after the grid mesh required for calculation is generated. It's not necessary to manually go through Fill Block, Fill Grid and Fit Grid, as Calculate system will automatically perform these operations one after another to run the analysis. However, it would be advisable to perform these 3 steps manually as you can visualize the output at each stage and identify if there are any errors in the geometry. Also, suppose you save the file and close it. Upon reopening, SOLIDO opens the project in wireframe mode. So you need to be at the Fit Grid to visualize the previously performed calculation. If we click on Text Output, under the Input Data tab, we see the parameters used for analysis such as the grid used for analysis and the material conductivities. Under the Calculation Results tab, we can see the total number of nodes analyzed, along with derived thermal parameters. Here you notice the 2D, 3D surplus and U equivalent, depending on which outputs were chosen before at the Edit menu, in Derived Thermal Properties. Notice that 2D 3D surplus is a generic output that depends on the geometry. Both can correspond to the linear thermal transmittance or point thermal transmittance or a combination of both, as in this example. Here you notice input data such as boundary temperatures and flanking element information for calculations. Here we also see the minimum and maximum temperatures for each material. You can now close the text output window. Then, click on Graphic Output to better visualize the results. Using Fill Temperatures from the top toolbar, we can visualize the temperature field in the cross-section. Click on Triangulation Mesh to see the mesh used to perform analysis. The software calculates the temperature at each node of the mesh and does a linear interpolation between these nodes. If you want to turn off the triangulation mesh grid, click on the icon again to deselect it. You can also render isothermal lines by clicking here. To explore the settings of these lines, click on the temperature range at the top toolbar. The maximum and minimum temperatures for analysis are taken from external and internal environments. If required, you can change this by unchecking Use boundary condition temperatures and input temperatures. Here, the first increment is represented by a pink isothermal line at the graphic output and the second increment is represented by a red line. You can set the single value isotherm, say we wanted to highlight the line at 10 degrees. Click on OK and close the dialog box. You can choose to fill off to clearly see the isotherms. You cannot distinctly see the single value isocurve line. This is because it overlaps with other isocurve lines. You can change this by clicking on Line Styles. Here you see the color assigned to isothermal lines. For a single value line, change the line width to 3 for example and the color to green. Upon clicking OK, you can now distinctly see the single value isotherm. You can also fill with Material Preview where you see conductivities in ascending order at the index for each material. You can turn on heat flow lines and turn off isothermal lines to visualize heat flux. You can zoom out and view the entire geometry if you click on Zoom Total, and to save the image click on the Save icon here. You can spend some time trying each option in this graphic output to see which combinations suit best for your visualization. We can now close the graphic output. Thank you for watching, see you in the next video.